cut the music off early this time, but that's all right. Um, we left off last time looking at the first problem to apply some of the combinatorial solutions that we've been developing on with Hamiltonian. With the first problem that we looked at here is the Hamiltonian path problem, and I just want to reiterate that a little bit. That given an undirected graph G, we want to determine if there is a Hamiltonian path or not. And again, a Hamiltonian path is a path that visits every single vertex exactly once. So the motivation for that is, you're trying to, that you have all these tasks to do, and you have to do them all, right? So you have to eventually visit all of these vertices. The vertices represent tasks, or they represent cities that you have to go to. But of course, you want to make sure that you can do that. Can I go from this city to that city? Or can I go from that task to that task? Or something like that. You have to do them all. And is there even a solution? Is there even a path that I can visit them all exactly once without having to waste my time and backtrack and do something again, right? That's the basic idea. You can also look at it from the perspective of a cycle. A Hamiltonian cycle is a cycle that visits every single vertex exactly once and comes back to the same vertex that you started at. You can also look at it as an optimization problem. If you've got a weighted graph where all of your edges have some weight or your vertices have some weight or something like that, you want to traverse every single vertex exactly once, but you want to do it in an optimal way. You want to minimize your path. So again, if it's a bunch of cities that you have to visit, I have to visit these 10 cities. What order should we go in? Right now, geographically, it's probably easy. Are there even any routes? Like, can I go from city A to city B via this airline that I'm stuck with or something, right? So a lot of different ways that you can look at this problem as an optimization problem, as a decision problem, etc. And the solution that we looked at last time was we simply just generated every single possible permutation. And we observed that that's going to be order n factorial. But we observed that, hey, if we don't have to necessarily do that, right? We know that this is a Hamiltonian graph in that you can walk around the outside of this, and there is your Hamiltonian path right there. As another example here, does there exist a Hamiltonian cycle here? Now remember, a cycle is just a path that comes back onto itself. So is there a Hamiltonian cycle here? No. Why not? What can you immediately see? As humans, we can look at this small example and immediately see that there's no cycle. Why not?
You gotta pass through B twice.
Yeah. I've got this kind of bottleneck here, right? If I start somewhere over here on this side of the graph, then I necessarily have to go and explore the entire other graph, but then I eventually have to come back, and because it's a cycle, I have to come back where I came from. And so this is my bottleneck right here. So we can say, for certain that there's no Hamiltonian cycle. There is a Hamiltonian path, of course, again, like we just described. But the naive solution of solving either one of these versions is not going to, it does a lot of extra work, right? Remember that last time we observed, let me go ahead and move this up here. Come on, move over. There we go. So we observed last time that if I took a permutation where there was a instance of DC in it, right? There is no edge connecting DC. Now, in general, how many permutations are there here? That if I go with n factorial here, this is going to end up being 6 factorial. Anybody know what that is? What was that last time? 720, right? So I have 720 possibilities that I have to enumerate and verify whether or not this thing is a valid path or cycle, right? But what if I consider anything with DC here, right? How many possible permutations involve DC? Well, if I have DC, A, B, no C, no D, E, and F, right? Now I'm permuting 5 things. Just take this thing and call it X. and you're dealing with A, B, E, F, X, you're dealing with 5 things now. How many possible permutations are there with 5 things? 5 factorial, right? So immediately by saying, well, by looking at the structure of the input and saying, there's no edge there, I can immediately get rid of, how many is that? 120 possibilities, right? So I've gone down now to only 600 things that I have to do. But wait, there's more, right? CD. Do I have to consider any permutations with CD in it? Nope. So how many more are there? 120 factorial. Now I'm down to 480, right? I'm cutting things down by looking at the actual structure of this. And by the way, that was just one edge. What other edges aren't there? A, C, A, E, A, F, right? Right? Yeah, so 1, 2, 3 times 2, 6, something like that, right? Now I'm thinking that these aren't exact, but whatever. 6 factorial, 1, 2, 3, 4, 5, 6 factorial, right? Oh, we're cutting it down by some factor, right? It doesn't matter, whatever the details may be. So what I want to do is I want to consider the actual structure. And the way that I'm going to look at this graph is I'm going to start at a vertex and I'm going to walk around it. I'm going to say start at D and start walking around and until you find what you're looking for, until you find that Hamiltonian path, or you hit a dead end. For example, if I start at B here and I go over to A, then I go over to D, what options do I have left? Can I go back to B? Nope, because then I would have visited B twice. So I'm at a dead end here. When I reach a dead end in a maze, if I'm exploring a maze and walking around in a maze, what do? You back up, right? You back up and oh, I took a wrong turn. I went down that corridor, that left corridor. There, that led to a dead end. Okay, back up and then go down that right corridor instead. And so what I'm going to do is I'm going to end up walking around this this graph here. Now, so let's go ahead and start at B. Right? Now, naively, we know immediately that there's not going to be a solution involving B, right? But let's go ahead and look and see what that looks like, because an algorithm, a dumb computer, doesn't know that there's not going to be a solution starting at B. But let's go ahead and do it. Right? So we'll start at B here. Now, what are my options? Where can I go next? Can I immediately jump over to F? Nope, because there's no edge there. Right? I'm taking the structure of the input into account here. So what options do I have? Where could I go? I could go to A, or I could go to D, or I could go to C, or I could go to E. So in order here, A, C, D, E. Those are all my options. Right? I could do any one of those things. Okay? Now, what is that called, by the way? Hopefully we have some terminology here. If I look at all the vertices that are connected to a particular vertex, what is that called? If you live in a house and you look at all the houses that are connected right next to you, what is that called? Just the adjacent houses, not the entire area. The one right next to you is your neighbor, right? So these are neighbors of B, okay? And we use that term here in graph theory, okay? So I start at B. Well, let's go ahead and consider this computation path right here, where I start at B and I choose to go over to A. Right? You need to keep track of it somehow, so I'll go ahead and go over here to A. Now what are my options? I could go from A, I could go to B, or I could go to D. Should I consider going back to B though? No, why? Because that would be backtracking, right? I went from here to here. Should I go back? No, that's not a simple path. Right? Remember, a simple path traverse, and besides, I visit the same vertex twice, and that's not a Hamiltonian path. Right? So if I'm at A here, I look at the neighborhood of A, and it's B and D, but B is out because I've already visited it. Because I look back, and that's where I came from, right? So my only other option here is to go to D. So let's continue that idea. Suppose that I went to D, at which point we've got a dead end, right? So I'm going to backtrack. I had no other possible corridors to go down to in the maze, so I'll backtrack up here, and I'll start all over. Now I am at B. Let's explore by going down to C. Right? So what does that look like? Let's go over to C here. Now I'm looking at the neighborhood of C, and I see that that includes B, E, and F. But B is out because that's where I came from. So continuing down, from C I could go to E, or I could go to F. We'll go ahead and be systematic about this. I started at B, I went to C, let's go ahead and go to E next. Notice here I'm just going in lexicographic order, in alphabetic order. You can go in whatever order you want. So suppose that I went down to E. Okay. What are my options now? Again, I look at the neighborhood. I could go to B, I could go back to C, or I could go to F. I don't want to go to B because that's where I came from. I don't want to go back immediately to C because that's where I came from. How did you get to E here to begin with? You traveled down this path. So my only option is to go to F. And so I will put that, I will put that right here, F. At which point, what? I've reached another dead end. By the way, is the path that I've formed so far from B to C to E to F, is that a Hamiltonian path? No. For a Hamiltonian path to exist in this particular graph, how many edges must it have? There's 1, 2, 3, 4, 5, 6 vertices. So to connect them all together, you would need how many? 5. Right? And this is of length 1, 2, 3. That's not it. Right? So let's backtrack. If I backtrack up to E, then remember that I only had one option to begin with. So backtrack again and consider going to F instead. And what does that look like? It looks like I went from B to C, and then I go over to F instead. And now I'm right here. So a path of 1, 2, length 2 so far. Now I look at that neighborhood. Now, yes, I visited E before on some other computational path here, but that's not my current computation path. My current computation path took me from B to C to F. And so E is indeed an option. But at that point, again, I face another dead end. Right? Because I do have things that I could go to, but there are things that I've already visited already. Right? So back up, and you can kind of see what this entire computation path is going to look like. Off of, so more quickly here, off of B, I can go to D, and then I can go to A. Right? But then I would end up backtracking all the way to B. If I decided to go to E, once I'm at E, I could go to C or F. Once I'm at C, I could go to F, and once I'm at F, I could go to C. Do any of those computation paths result in a Hamiltonian path? No. Why? Because I started at that bottleneck right there. But we know that there is a Hamiltonian path, right? I just have to restart it at a different starting point. Give me something to start at. A? Okay. If I went from A, then I looked at its neighborhood, and I won't go through the full details here, but B and D. All right? Suppose that I went over to B. From B, I could go to C or D. If I went to D, then I would be done, and I would be at a dead end. If I went to C, I would have options to go to E and F, and from there, I could go F and E once again. Are any of those Hamiltonian paths, by the way? 1, 2, 3, 4. Nope, nope, nope. So backtrack, backtrack, backtrack. If I went from A to B to D, A to B to D, that's a dead end. So if I went from A to D, what are my options now? I could go to B, right? And there. That's what it looks like so far. From that, I can go to C or E. If I went to C, oops, sorry. If I went to C, then I could go to E or F. And from F, or from E, I could go to F. At which point, stop. What have I discovered? 1, 2, 3, 4, 5. There's my Hamiltonian path. Do I need to explore the rest of these things over here? Nope. Not unless you're trying to find every single Hamiltonian path. If you want to count the number of Hamiltonian paths, if you want to find the best Hamiltonian path, whatever that means, then yeah, you would want to explore and go on and search for more Hamiltonian paths and then compare them. Well, here's a Hamiltonian path that I found so far. I found another one. Is this one better in whatever measure or objective function you're trying to achieve? But if I'm just trying to answer a yes or no question, at this point I'm done. Right? What was I doing this entire time? I hit a dead end. I backtrack. And that's the idea behind this, algorithm. It's still brute force, because ultimately I am doing, in this particular case, I might end up doing an exponential amount of work, but I'm not doing the naive approach of every single possible permutation. I am taking the structure of the problem, the structure of the input actually, into account. Okay? That's what backtracking is. You iteratively try to build a solution instead of blindly going at it. Right, so let me go ahead and start making notes here. So generating combinatorial objects is blind problem solving. You're not taking any other structure into account. Often we need, or it is better to take the structure of the problem or the input into account. Right? We like structure. What is the tentative title of this course? Computer Science 3, yes, but the official title is Data Structures and Algorithms. Why do we like structures? Structure can be exploited. If we can exploit that structure, we can develop better data structures. We can develop better algorithms, more efficient algorithms, right? Generally, brute force backtracking, is not necessarily better asymptotically. If what you were doing was exponential before, what you're doing now is probably going to still be exponential. But you can severely cut down the number of operations that you actually have to do. Yeah, go ahead. Question?
It wouldn't still be n factorial though because we're cutting those out, or would it still be?
There's a conundrum. Now you have to take your structure. If you want to analyze this, you have to take the structure into account. Because the worst case scenario is where you end up generating every single possible permutation, right? Which means that you have a complete graph. But ironically, if you have a complete graph, the very first computation path that you find, there's your Hamiltonian path, right? Now it's a different story if you're trying to generate every single possible permutation path. But then you can check, is it a complete graph? And answer immediately that there are n factorial of them, right? So there's something in between, just like n choose k looks like it's a constant, looks like it's a polynomial, but then when you look at the average or the middle case, basically, right? What I just described were extreme cases where you get lucky because you find something immediately, or you get unlucky, or in the middle is where you get unlucky and you end up having to do an exponential amount of work anyway. Okay. And yes, there can be exponential many computation paths even when you're doing backtracking like this. Yeah. It does not cut it down to polynomial. That would collapse P and NP, and we have no idea if that happens, right? So it doesn't necessarily mean that it's going to be better asymptotically, but in practice, it can save a lot of work and make exponential algorithms more feasible. more feasible. I'm not going to go so far as to say that they are now feasible, right? So what's the general technique? The general technique is, well, it's going to be different for everything that you consider because you're exploiting the structure, right? You have to look at the problem. What does backtracking look for like for this particular problem, for this particular input? But generally, you iteratively, right? And in this case, we're going to present it as recursively. Recursively, build a partial solution. By the way, forgive me for bad typing today. My butterfly keyboard that has now been replaced for the third time is now dying, and I have no D button right now. I have to, so I'm gonna have to, really whack that that sensor right there until you reach a feasible solution, or you reach a dead end. Dead end, you see, right? At which point you backtrack. Right? If I can think of words off the top of my head that don't use D, alternative words, then we'll be a lot better. Right? So again, the example that I like is walking a maze. Right? You keep track of where you've been. Those are called breadcrumbs. Right? You or you keep a string, right? Because if you're in a labyrinth, if you're in a maze, how do you know where you've been so that you can backtrack? If I backtrack from a corridor and there are 5 alternative doors around me, I have to remember, well, okay, I've already explored that door, or I came from that door, so I don't want to go back that way, right? You need some way of keeping track of those breadcrumbs. Once you hit a dead end, you back up and you take a different route, right? Or chess, right? Or in a computer AI, it's not really artificial intelligence, right? A computer AI player will simply look ahead, right? And cheat. Look ahead and choose the best possible move. Right? It's not that playing computers are smart in the traditional way that we think of intelligence as human intelligence. They're just very, very good at automating things. They can look ahead 1 million moves, right? Okay, well, if I make this move, then they've got me in check in 5 moves, right? Or there are a whole bunch of outcomes. 90% of them result in my loss. Okay, well, if I made this this choice over here, then 90% of the outcomes resulted in my win. Which one do I go? That way, right? And you're only able to do that by looking ahead and choosing which computation path to go to first. These are all computation paths right here, right? That there was some computation path that took me down here, and then I backtracked up. This is a computation tree, right? It's not a binary tree, but because things can have more than one child. In this case, it is a binary tree, I guess, but it's not a binary search tree. It could be much larger, right? In fact, if we go off of D here, 1, 2, 3, 4, they're going to be, or B, sorry, up here, there were 4 children. So clearly it's not a binary tree. But it is a tree. It's a computation tree, and that's what we call it when we look at it from this perspective, okay? Now, let's go ahead and codify this. In other words, let's go ahead and come up with some pseudocode that describes the solution that we just came to, okay? Now, to do that, we, of course, should be a little bit more exact. So what I'm going to do is I'm going to split it up into 2 pieces of pseudocode. The first one I'm going to call a DFS Hamiltonian walk. All right, main. And I'm going to split it up for a reason here. All right. Remember on this example that we just had, was I successful when I started at B? Nope. Was I successful when I started at A? All right. Well, did I know to start at A? Well, you knew right away by looking at the picture. But a dumb algorithm, a dumb computer, could they say, "Oh, well, don't even try that thing," because it won't result in any success over here. Go ahead and start at A. No. So you have to be systematic about it. You have to potentially start over at each potential vertex, right? So that's why I'm going to split this up into a main, right? And my input here is going to, of course, be a graph. G equals V, comma, E, right? And my output is going to be true if G contains a Hamiltonian, and here I'll start abbreviating Ham path. You can adapt this very, very easily to do a Hamiltonian cycle. You can adapt this very, very easily to count up all the Hamiltonian paths or cycles. And therefore, you can update this or modify this to find the best Hamiltonian path or cycle, right? So this is basically just the main algorithm where I potentially have to start over each time, right? So for each vertex, V in V, right, that's going to be my starting point. My path will end up being just V. I start at V. It's a single vertex. And then I'm going to call this other algorithm if walk on G, comma P, and we'll describe what this is in a second here. Then what I'm going to do is I'm going to output true. Excuse me. There we go. Sorry. Output true. Okay. Otherwise, if I get through every single possible starting point here, I think I've got a typo here in the notes, but that's okay. I'll fix it later. For each vertex, if no vertex ended up with a Hamiltonian path, then I would end up outputting false. Okay? So now what does walk look like? You can see that this is just a main. I have one vertex as a starting point, and then I need to walk around the graph to determine if there's a Hamiltonian path. So this is what we're going to develop now as my second algorithm, right? As my subroutine, if you want. So this will be walk. G, P, right? My input here is going to be two things now. A graph, G equals V, comma, E, and a path, P, right? Okay, and my output here, and I gave this a name, by the way, because again, we're going to present this as recursive. So obviously I'm going to be calling this function on itself. And my output here is going to be true if G contains a Hamiltonian path. False otherwise. Yes, no, what, if you want to use those terms instead. And you can see now the way that I use this over here, if my starting point V ended up with a Hamiltonian path from the subroutine, then there's no reason to continue this for loop up here. And instead, I can just stop and immediately output true. Okay? All right, so what does this look like? Well, again, let's go back over here to the visualization. And let's think about it in general. I'm in this graph here, and I came from somewhere. I started for somewhere, I came in this path, and now I'm at the current vertex here. Right? Let's go ahead and call this current. In fact, let's give it just an even easier name. Let's just call it X. Okay? This vertex right here. Now, what are my choices? What are, for continuing to explore the graph? I look at the neighborhood of X, and I systematically go to each one of these things, as long as I am not backtracking to something that's already in the path. Okay? So all I need is I'll call it Y in, actually I'm going to have to set X here. Set X to be the last vertex in P. Right? For Y in the neighborhood of x. Right? Now here's my annotation of this. N sub x is equal to the neighborhood of x. Right? It's just all the vertices that are immediately adjacent to it. Okay. For each one of those x's or y's, if y is not in the path, then I call the walk algorithm again. Walk on g, but now I have, so g doesn't change, right? That's the input. But remember, now I'm on the path. I'm on this path. And there's this y over here. So I'm going from x over to y. So my new path is going to be what? This path that it took me to x, then add y, and then continue. Then you repeat and find y's neighborhood, but you let the recursion do that for you. So my updated path here is going to be p plus x. Right? Now I'm slightly abusing notation here. I'm just borrowing concatenation. Obviously, if you were to do this in, say, Python, you would probably want a list, and then you would append to that list or something like that. Right? Note here that this does not change p. Right? That when I backtrack, right, when I've got, here's x, and I go to y, when I backtrack, I don't want to have y still on the tail end. I want x to be on the tail end. This right here is not modifying the path, p. So that's a programming issue that you'll have to come up with, not this Friday, but next Friday. A programming solution that you'll have to come up with. How do I do this? Well, you just take a list and you append it. When you come back from your recursion, if you use recursion, then just pop off the last thing that you did, right? Basically what we're doing is we're using a stack here, but we're using recursion, we're abusing the call stack to keep track of our breadcrumbs. Okay? All right, so if this is not in there, then I go and take another walk. Okay. Now I don't see any returning of true or false here yet, do you? So we have to think about that. When do we have a Hamiltonian path?
When the length of our path is n, or
the length of the path is
the size of g minus 1?
the size of the number of vertices minus 1. Right? So let's make that our base case. And that's why I left some room up here. If the length of the path is equal to the size of the vertex set, the cardinality of the vertex set, minus 1, right? So again, annotations over here. This is going to be the length of the path p. And hopefully you're already familiar with this. Right? I'm just borrowing that notation from set theory. This is the cardinality of v, right? So if that's the case, then we have a Hamiltonian path, right? And we can stop and output true. Okay. Now, what about the opposite condition? When do we know that, starting at b results in no Hamiltonian path here at all? I tried every single possibility. Each one of those possibilities tried every single possibility. Each one of those possibilities tried every single possibility, and none of them ended up returning true or outputting true. So where do I output false? After I've tried every single possibility, every single one of those possibilities have tried every single possibility. After all that's been done, I output false. Or no, there's no Hamiltonian path. At least given the current path here, there's no Hamiltonian path that emanates from that path. Okay? And again, this is going to be kind of difficult to analyze exactly. You can think about this in worst case scenario where order n squared, or it's not n squared, order n factorial, right? But again, it's kind of on a spectrum here where if you actually end up doing order n factorial, then the first one you find is going to be the Hamiltonian path, right? Think of it as n factorial divided by 2. Is that any better? Asymptotically? No. Think about it as n factorial divided by n. Is that really any better? No, it's still factorial. It's still exponential, super exponential. Right? Okay. So any questions on that pseudocode? Otherwise, you'll be programming it in, well, not this week. By the way, if you are teaming up in pairs, I highly encourage you to do so because it means less grading for me. But if you do, make sure that you're going into Canvas and teaming up with the under people, those pairs, and following all the instructions in the handouts. All right? Yeah.
So when if we want to make our own pseudocode, or we will make our own pseudocode for like this upcoming assignment.
Okay.
If we have like multiple functions in our program.
If you want to split up your pseudocode into multiple different algorithms, that's fine. That's perfectly fine. Just make sure that you're not losing the forest for the trees when you analyze them, right? If I said wrote some pseudocode like selection sort, and then as a subroutine find min, and I say find min, that's my elementary operation, right? And then it makes selection sort look like a linear time algorithm, right? Because you're hiding additional comparisons in that subroutine. So make sure that you are analyzing it correctly if you do that, right? Okay. Yeah.
I was confused about you assign the last vertex in P to X.
Where? Here?
So the last vertex in P.
Oh,
Oh, yeah.
the last vertex in P. So if you've got this path that goes from A to B to C, or C, and then D over here, right? And this entire thing here is P, right? The path P. What was the last vertex? D, right? Because a path is ordered, right? It can't be, well, B, C, A, D, right? That's a completely different path. So this is ordered. Just take the last one. Right? Yeah.
But if X is already the last vertex in P, why do you need walk to add X to P?
Oh, sorry. Thank you. Good eye.
That's what
Good
I'm
eye.
confused too.
I'll even use red there.
Now I understand.
I'll even use red there because well, I'll use red when grading. So I'm grading myself here, right? So sorry about that. Yes. It is correct in the notes, or in the note deck there. Okay. All right. So let's look at another problem. All right? And this is what we'll end with here today. We'll just, oh yeah, go ahead.
Do we have a spot to where like oh no, wait, since it's recursive, it'll just pop off.
Yep, you're using the return, the output in this case. I'm not using the keyword return because I want to keep it pseudocode-y, right? But you would return true or false, right? So we're all thieves, right? So what's a thief's motivation? Get as much money as possible, right? So we break into a store, and we see, it's a precious metals store, right? And we see a bunch of gold, and we see a bunch of platinum, we see a bunch of iron, and we see a bunch of steel, right? Like steel, not steel as in you steal it, and then I don't know, a bunch of calcium dust or something. What are we going to go for? Are we going to go for that iron and that calcium? No, we're going to go for the precious metals, right? So, but can we carry absolutely everything? We gotta break and dash, right? We gotta take as much gold or platinum. Which one is worth more? I think gold is by weight, right? If I can only lift 50 pounds or whatever, then do I take 50 pounds of gold or do I take 50 pounds of platinum? I think gold is more valuable, right? So we always go for the most valuable thing. Let's set up a scenario in which we make that kind of decision. So we've broken into a store here, but there are only 4 items. It's a small store, right? Because I don't want to write too many things down. We've got 4 items here, and it could be metals. It could be, you steal the cash because you can carry way more cash per pound than gold, I think. I'm not sure. Well, no, per troy ounce, what isn't gold like $3,000? But the $3,000, if it's all hundreds, would be way easier to carry, right? So
Maybe
I don't know.
just get gas. It's pretty expensive right now.
Gas. Well, a pint's a pound the world around, so I'm sure that the density of gas is not the same, but you're carrying water at that point. Definitely not worth it. So each one of these things has a value. Say that this is $15, this is $10. We're not very ambitious thieves here. $5. 1, 5, 3, and 4 are the weights. They're pounds. And suppose that I'm very, very weak. I have a maximum capacity of 8 pounds. I can only carry 8 pounds. All right, so you tell me your strategy by just immediately looking at these things. What are you going to steal first? A1, okay. Now, what's our value so far? 15, and our weight is 1. So what's remaining? We can carry 7 more pounds. What do we steal next?
A1.
We already took A1, right?
Oh, okay.
This is, so I'll just give you what this is called. This is my knapsack. I'm putting they've got that sack with the dollar sign on it, right? We're putting stuff into it. No, it's just a cartoon, right? So so here's my knapsack. I'm putting all this stuff into that knapsack.
Being pretty devious because it's not actually money in there. It's gold.
No, it's not money, no, but it's valuable stuff that we can hawk for money. All right, what do you steal next? Again, you can only carry 7 more pounds now. A3? Okay, you want to do A3? Okay. That's $9. 3, and now I've got 4 pounds left over. So can I steal A2 now? Nope. So steal A4, and you've got 5 and 4, and now you're at your maximum capacity. Your stealing is done, run out before they catch you, right? So this is 20. This has a value of 29, right? You guys are smart about it, but a thief that's not that's greedy and not at all quick-witted, what are they going to do?
A2.
A1 and then A2 because it's the most expensive thing, right? So 15 and 10 with a weight of 1 and 5, 6. Can we steal anything more? Can we steal A3 or A4? Nope, because that would exceed our maximum capacity up here. And so kind of a naive, dumb thief would only get $25 out of the deal. Right? You guys found the better optimal solution because it was so small and you looked ahead and you probably thought in your head, well, if I got something that exactly added up to 8 pounds, that would probably maximize my profit. Even that strategy is not going to work for you in general. Right? Being greedy about it, like this person, and even maximizing your weight capacity is not going to lead to optimal solutions necessarily. This is called the 0-1 knapsack problem. Right? So another problem here, the 0, and I'll just write a 0-1 knapsack problem. Now, why do we call it 0-1? You can take something or you can leave it. Taking it, 1. Leaving it 0. It's not like it's a jar full of gold coins where you can steal as many gold coins as you can carry and then you're out the door, right? You have to take the whole jar or nothing in the jar, right? So it's a 0-1 knapsack, okay? Oh, do I not have it described here? Okay, here we go. So I will go ahead and copy this over for the sake of time. Oops. So given a collection of items, A, and we just number them A1 through AN, we don't know what they are. Each item has a weight, W sub I. Each item has a value, V sub I, as I wrote down. Our knapsack has a maximum capacity of K. We can only carry at most 8 pounds, right? What we want to do is we want to steal as much as possible subject to our weight capacity, right? In other words, we want to maximize to maximize the sum of the values of all items we take, but the sum of all weights of items we take cannot exceed, what did I use, K? There. There we go. All right. And as I've already noted, the greedy approach is not necessarily optimal. The attempting to max out your weight capacity is not necessarily optimal. Right? Instead, what's a combinatorial approach? How could I solve this problem? I could consider all possible knapsacks, right? And in mathematical terms, what does that translate to? What combinatorial objects do I want to generate? So there are 4 items here. I could take the first 2, or I could take the last 2, or I could take the first 3, right? Or I could take one item at a time, singletons, right? Or I could take nothing at all and be a good thief, as a morally good thief. You're a terrible thief if you don't take anything. So what am I generating? Combinations. Generate every possible combination, right? That is subset, right? If the sum of weights exceeds K, it is not a feasible solution. And so you reject it, right? Otherwise, among all feasible solutions, you choose the best one. That is the maximum sum of values. Okay? Do we know how to do that? Yep. We already know how to generate combinations, so we could leave it at that. But now, think about backtracking. What might backtracking look like?
Horrific.
Well, not necessarily. What if I took A2 and A3? Sorry. Here's another solution. A2 and A4. What's the weight there, the total weight? If I took A2 and A4? 9, right? I'm already infeasible. Do I have to consider then subsets that took A2, A4, and A1? Nope, because just by simply taking these 2, I've already reached an infeasible solution. Do I have to consider any subset that takes A2, A4, and A3? Nope. Do I have to consider A2, A4, A3, and A1? Nope. Right? But now, if I could carry everything, then it would be kind of a trivial instance of the problem. You could go through very easily, add up all the weights, and if that's less than your weight capacity, then you could immediately say, all right, just take everything and we're done. We don't have to consider all possibilities, right? But here is where my backtracking or pruning comes in. Again, we're going to look at this as a computation tree. And if this computation path becomes infeasible, do I need to consider anything hanging off of that path? Nope. So, like a good arborist or whatever tree people are called. Yeah, they're arborists, right? Once I get to an infeasible solution, I can prune that branch of the tree out and not consider it at all. If I've got this big, giant, exponentially sized tree, and if I prune enough of it, then what does that tree start to look like? A stick, right? And if it's just a stick, I can compute a stick, right? Sorry, abusing all these arborist terms or whatever, but you get the idea to give you an intuition. When we come back next time, we first have to understand how can we generate subsets recursively, and then once we've got that idea, how can we incorporate the actual structure of this problem so that we can prune things out and not have to worry about the entire tree. Okay? All right. I'll see you on Friday. remember, you do have your first assignment due on Friday. At midnight, if you team up, make sure that you're teaming up in Canvas. Written portions are PDFs and to Canvas, and your programming portion is through WebGrader. All right, I'll see you then.